Hey, so we've done this problem before, but I think it's good to go back and review. This is going to be a good representation of a mean value theorem, trig derivatives, average rate of change topic that we'll see on the test. So on page 2, number 4, an object's position is given by f of t. It's continuous and differentiable, so we know it's a smooth curve, no breaks in the graph from 0 to 3 pi. F of t is given in meters. Find the average velocity. So average velocity or average rate of change. That means just find the slope between the endpoints. So no calculus, no derivative. Anytime you see a word average or average rate of change, that's talking about just slope. So here's my position function. So anytime we want to work with a trig function that is written in this specific form, what can we do to make it easier for what we want to do with it? Yeah, but brackets around. Now, the bracket's going to go around the 2, or is it just the secant? So it helps a lot for derivatives, but also for evaluating. It kind of helps us see where that 3 belongs, and it doesn't mess with your order operations and throw you off. So, okay. So part A, find the average rate of change or average velocity. So if it's asking for instantaneous rate of change or instantaneous velocity, then that's derivative, right? For average rate of change is change in that value over the change in the time. So average rate of change between 0 to 2 pi. So we're going to do f of 2 pi minus f of 0 over 2 pi minus 0, right? Just change in value over the change in time. That's rate of change, or another word, slope. Okay, so that means we have to find the endpoints so that we can actually plug this in, right? Okay, so f of 0, I'll enter 0 in for t. Okay, let's think about our unit circle values. We may not be as familiar with secant, but we're pretty good with cosine, right? So what's cosine of 0? Unit circle values. Yep, cosine 0 is 1. And if I flip 1, because I know secant is the reciprocal of cosine, what do I get? What happens if I were to flip 1? You still get 1, right? So 1 cubed is 1, 1 times 2 is 2, so there, okay, f of 2 pi. Secant of 2 pi is same thing as secant of 0. And so we should get the same results. Well, it's asking. You're right. My bad. 2 pi over 6. What's that? Right. Yeah. So 2 pi over 6. Back into the original function, which is pi over 3, and secant the pi over 3. We may not be as familiar, but or we know cosine of pi over 3. Cosine of pi over 3 is yep, so that means if I flip it, it becomes 2. 2 cubed is 8, 8 times 2 is 16, so okay, so I'm ready to find my average rate of change in my y over the change in x, or average velocity in this case. Okay, 14 over 2 pi, that reduces to be just 7 over pi. Units of measure is what? Meter per second, okay. For B, at what point does the instantaneous velocity equal the average velocity? So instantaneous velocity, that's just the derivative, that's just the velocity function. So we just set up the equation like the way that they're asking for us to. Equal to the average velocity, so we have that. So that's 7 over pi. So we're looking for when is velocity equal to 7 over pi. And this is really just another rewording of mean value theorem. Mean value theorem is when does the average rate of change equal to the instantaneous rate of change. So we're just looking to set this up. Set up where velocity is equal to that average velocity. Okay. So we're on page 2 in your packet, the original packet. We've done this already. We're just redoing the same problem that we've done in the past. Page 2 in your packet. Okay, so I want to build my velocity function. So to build my velocity function, I have to find the derivative of position. So what's involved here if I want to find the derivative? Chain rule, right? So having that rewritten with that bracket and the exponent on the outside for a lot more, that's a lot more clear how we're going to build this derivative. Okay, so okay, so to find the velocity function, I have to find the derivative, and we say chain rule. Outside is that 2 bracket cube. And the inside is that secant of u. I can rewrite that q over 6 in a way that's more familiar or easier with our fractions. So I'll say 1/6 t. We're on page 2 of our test review packet. Okay, so f prime. Outside derivative, we take that 2 bracket cube, becomes 6 bracket squared. Keep the inside intact. Times the inside derivative. Okay, so secant of u becomes secant u tangent u times u prime. So u prime is the derivative of 1/6 t, which is just 1/6. So we have our derivative, we have our average velocity. So we're just going to set them equal to each other. That's it. It's not asking for us to solve, it's just asking us to set it up. So we have this piece, we have this piece, set them equal to each other. Okay, I could do some cleanup here. The 6 and 1/6 can reduce. I can merge the secants together here. So there's two secants here. There's another secant there. I can make that secant cubed. Next part is what is the instantaneous velocity when t equals pi seconds? So we can just use the velocity function and plug pi in and find that value. There's my derivative. I can just plug in pi in for t. Okay, secant of pi over 6 may not be as familiar, but we know cosine of pi over 6 is root 3 over 2. So if I flip that, I can get secant, right? 2 over root 3. Cube that. Tangent of pi over 6. Tangent of pi over 6 is y over x. You look at your thing about your unit circle value here, order pair. There's my order pair for pi over 6. My tangent is y over x, so 1 over root 3. If I clean this up here, I get 2 cubed, which is 8. Root 3 times root 3 times root 3, that's 3 root 3. There's another root 3 sitting out here. So root 3 times root 3 is 3. 3 times 3 is 9, so 8 over 9. As we're on page 2 of the test review packet, we've done this problem already, but we're just kind of going through and revisiting this problem. Okay, what is the instantaneous velocity when t equals 2 pi seconds? So same idea. Take our velocity function, insert 2 pi. So secant of 2 pi over 6, the same thing as secant of pi over 3. Maybe we can think in terms of cosine of pi over 3 first. Just some of that feels more familiar. Cosine of pi over 3 is 1/2. We take that 1/2, we flip it, we get 2. To get to the secant, so 2 cubed. Tangent of pi over 3, tangent of pi over 3. Root 3 over 1, right? Okay, so 2 cubed is 8, 8 root 3. There's our f prime of 2 pi. Okay, part E. Okay, find the equation of the tangent line to the graph at 2 pi. So tangent line equation, we need order pair, we need slope, so we have everything. Almost everything that we need. We still have to find our order pair at 2 pi. So we can insert 2 pi into the original function. Get back into the original function. I'll do 2 bracket secant t over 6 cubed. Okay, so secant of pi over 6, 2 pi over 6, sorry, same thing, or related to cosine of pi over 3. We know cosine of pi over 3 is 1/2. We flip that, we get 2. 2 cubed is 8. 8 times 2 is 16. So, right, so I have my order pair and my slope. I can just pull that from part D. Okay, point slope form. I use t here just to match that t variable there. Okay, let's do a full curve sketch problem. So we've done this already, but I think it's good for us to do again. This is page 6, number 6. You mean the video? Yeah. Yeah. Yeah, if you can't find, yeah, it'll be under today's date, so you should be able to see that. Okay, 1/2 x minus cosine x from negative pi to pi. Number 6, page 6, everyone okay with that? So we've seen this already, but we're going to try to work through again. So move directly into the derivative so we can find our critical points. Cosine becomes negative sine. I have 2 negatives. That's positive. Set equal to 0. Could be negative 1/2. Sorry, you're right, negative 1/2. Thanks. Okay, so sine equals negative 1/2. Think about the original kind of unit circle values that we can adapt to our domain a little bit later. So sine is going to be in the third and fourth quadrant. Going to be in that pi/6 family. No, you gotta draw a blank one on your own. Yeah, so I can give you a unit circle now if you want to just have that for now, but tomorrow I'll put it here. Yeah. Okay, so 7pi/6, 11pi/6. Now the problem is that this is normally fine if it's from 0 to 2 pi, but our interval is from negative pi to pi. So let's just think about our number line here, right? So pi is over here. 7pi/6 is outside of my interval, and so is 11pi/6. I need to land between negative pi and pi, so these are not quite inside my interval, but I can always find something related, coterminal angles, by subtracting 2 pi, right? So if I subtract 2 pi, or minus 12pi/6, match common denominator, right? So 7 minus 12 is negative 5. So negative 5pi/6, or negative 5pi/12. It's 5/6, no, not 12. Negative 5pi/6, that fits nicely to the right of negative pi. And if I subtract 11pi/6 minus 12pi/6, I get negative pi/6. Okay, so those two related coterminal angles or values are sitting nicely between my interval, so I'm going to be using these. Okay, so here's my slope sine line. Okay, so we know our graph is going to be oscillating, but let's test some of these values here. So I can test 0 between negative pi/6 and negative 3pi/6. I think maybe I'll choose negative 3pi/6. That feels like a easy value because that's just negative pi/2. Okay, it's hard to find something here, but it's okay. If we have 2, then it should be easy for us to see the pattern. Okay, so if I insert 0, where am I going to test these values against? Derivative, right? This is my slope sine line. I want slope behavior, not ordered pair. So I want back into the derivative. Okay, so 1/2 in for x. Sorry, 0 for x. Sine of 0 is 0. 0 plus 1/2 is positive. So negative pi/2. If you don't recognize negative pi/2, you can always add 2 pi to see it's really the same thing as 3 pi/2. So sine of 3 pi/2 is negative 1. Negative 1 plus 1/2 is negative. So, okay. And we can't find something here. It's tough to find the special angle, but I already let you know it's going to be oscillating. So you can figure out one of them, you can figure out the others. Okay, so what do we expect here? Negative 5pi/6, we expect relative max, and here we expect relative min, right? Yeah. Okay, so we'll come back to that. We may have to revisit that, but let's get the calculus out of the way. Let's go ahead and find the second derivative, point of inflection, concavity, all that. So second derivative, f double prime. Okay, so we have to go one derivative down from f prime. So 1/2 turns into 0. Sine becomes cosine. Okay, we're going to do the same graph in class. Okay, we're just going to get really comfortable with all the things that we're seeing here. Okay. Okay, so we set our second derivative equal to 0. Ask ourselves, where is cosine equal to 0? So if we just think in terms of our unit circle value, cosine is 0, where pi over 3 pi over 2. So let's just consider that for a moment. Is that going to fit nicely in our interval? Maybe not perfectly, but we do see pi over 2 landing nicely. It's just the problem is that 3 pi over 2 is outside. So if I subtract 2 pi to get that inside my interval here, the same thing as negative pi over 2. And negative pi over 2 looks like that lands nicely inside my interval there. Okay, so I have my 2 critical points there that lands nicely between negative pi and pi. So I'll go ahead and create my concavity sine line. All right, negative pi. Okay, so let's see, find some values to test here. I can test 0. Between pi over 2 and pi, I can choose, let's say, 2 pi over 3. Here, between negative pi over 2 and negative pi, I'll choose negative 3 pi over 3. Okay, so I'm going to test against my second derivative function here. Start with easy one here, cosine of 0, that's positive. So talking about concavity here, so concave up. 2 pi over 3, that's second quadrant. Cosine in the second quadrant is going to be negative, so concave down. Negative 2 pi over 3, we know that is same thing as 4 pi over 3. If I add 2 pi, that's third quadrant. So cosine in the third quadrant is negative, so concave down. All right, so we are expecting 2 points of inflection, right? 2 points of inflection. Okay, so we're going to sketch our graph, and we're going to just try our best to do our estimations as best we can. We want to treat, okay, so we want to definitely insert the endpoints into the original function. We want to take these x values, these are important values, right? These are relative max, relative min. So if we can plug into the original function and get an idea where that y value is going to be. And that's also going to be really helpful in terms of estimating where our absolute max and absolute min is, right? So if we can have a picture of the graph, then we can just look at the graph and see, okay, that's obviously the highest point, that's the absolute max. You know, lowest value is my absolute min. Okay, so I'm going to take the time to plug in my endpoints, my relative max, relative min. The POIs are not as important because we know that once we sketch our graph, they're just going to land along our path of the graph. But what's more important are endpoints and relative max, relative min, because that's going to be allowing us to make our decision as to where our absolute max or absolute min. Okay, so here's my original function. I'm going to write that down here again. Let's just have easy access. So this is half x minus cosine x. Okay, plug in negative pi. Now, we're going to treat pi like 3 or negative 3. Okay, so, and I'll give that indication on the test as well. Like just treat, because without a calculator, the best we can do is estimation. So we just find the closest whole number and then just make our best estimation from there. Okay, so I'm going to graph is going from negative pi to pi. So I definitely want to know where these points are located so I can put them onto my graph. Okay, so negative pi over 2, that's the same thing as negative 1.5, around negative 1.5, right? If we treat pi like 3. And the cosine negative pi is the same thing as cosine of what? Pi, which is negative 1. So negative 1 times negative 1 is a positive 1. So we have an idea, it's around 0.5. Just ballpark value. You have to know the exact value to know where to graph. The other endpoint is at pi, so put that in as well. Pi over 2, that's 3, right? Fine, it's treated like 3. 3 over 2 is 1.5. Cosine of pi is negative 1. Negative times negative is positive. 1.5 plus 1 is 2.5. So we know our graph is going to start at 0.5 and eventually going to make its way up to 2.5. All right. The other two important points are relative max, relative min, because they're going to help potentially be a absolute max, absolute min. We want to know where they are. So we expect a relative what at negative 5 power 6 at relative max, right? And a relative min here. Okay, so negative 5 power 6. Okay, so again, we're going to treat pi like 3, right? So this is like negative 15 over 12. Cosine of negative 5 pi over 6, we know that negative 5 pi over 6 is the same thing as 7 pi over 6. So that's negative 3 over 2. Like a little bit more than more than 1, so like maybe like negative 1.1. And I'll give you that indication that root 3 over 2 is like around 0.7. So we know that it's going to be somewhere in that 0.2 range. Or negative 0.2. So sorry, 3.4. So we know it's going to be a little bit higher than plus 7. Let's see. My bad. Let me see. This should be at negative 0.5. Sorry, negative 0.5. So we know it's going to be slightly higher, but not much higher. So it's going to be barely above my starting point. Okay, and then I'm expecting a relative minimum at negative pi over 6. So I'm just inserting to the original function to get an idea where it lives. So think of pi as 3. So that's negative 1/2 times 1/2 is negative 1/4. So I'll do that negative 0.25. Cosine of negative pi over 6, that's, we know that's 4th quadrant. Same thing as 11 pi over 6, root 3 over 2 minus, like, negative 0.7 minus 0.25. It's around like negative 1. So definitely lower than all the other values. Okay, so if we have these 4 points, we should have a pretty good feel for how our graph's going to look. So here's my graph here. I'm going to start at negative pi. I'm going to end up all the way over at pi. Okay, so I'm going to start off at negative 0.5. Let me just go a little bit lower here. I'll say this is negative 1/2. This is negative 1 here. So I know my graph's going to start here. it's going to rise up to some relative max at -5/6. I think at 5/6, I'm expecting it to be not much higher, right? But I do know that it's still going to be that negative region here. So I'm going to target that point, call that -5/6. And then from there, it's going to decrease down to -5/6. That's a relative minimum. We knew that from looking at our sine line. And right now, I don't care about my curvature here. I just want to get my slope down. So relative minimum at -5/6 rises all the way up to pi, and at pi, my y value is at 2.5. So up here. So I want my graph to eventually end up here. Okay, but my graph should match what I expect for my slope. Positive slope, negative slope, positive slope. Okay, points of inflection, not as important because we can kind of just estimate where they're going to land. So -pi/2, there's point of inflection, pi/2. So -pi/2, we know is somewhere between negative pi and -pi/6. So I know somewhere around here. It's going to target. And then the other point of inflection is at pi/2. Pi/2 is between 0 and pi. So I'm just going to just target a point where I think pi/2 is. And now between all of those points, or between my points of inflection and my endpoints, I know I can just match the graph with the curvature that I expect, right? So I want concave down to go to -pi/2. Concave up to reach my next point of inflection. And then concave down to end my problem, to end my sketch. Okay. Okay, so absolute max, absolute min. We can tell our absolute max at this endpoint here. So I can say absolute max is f of pi, right? Which you can write it in this form, or you can just give that estimation there. It's around 2.5. And absolute min is coming from this relative min that we found that ended up being the lowest point. So -pi/6, which our estimation was around -1. And then for all these like unit circle fractional values that you may not be familiar with because you don't have a calculator, I'll give you an estimation. I'll say, √3/2 is, 0.7, and then you're just going to just use those values and estimate the best of your ability, right? I'm not expecting you to get the exact decimal right, just a ballpark value of where it's going to be. Enough to make a conclusion as to where the absolute max, absolute min is. Okay, everything else should on this page should feel a lot easier, especially if I'm asking for point of inflection. If I ask you for point of inflection, I'll just ask you for the x values. Intervals of concave up, concave down, relative max, relative min. You can pull all that just from your slope and concavity sine line. Okay, any questions? Yeah, so I wanted to use this help session to tackle what I think students are going to, have probably need most practice with, and that's curve sketching. So we did mean value theorem on page 2. We did curve sketching. So in class, I have another related race problem I want us to do together. We'll revisit the particle motion problem. We'll do an implicit differentiation problem that I have on the board. We'll review our derivative rules. And, we should be able to. And then tomorrow morning, I'll just, continue to revisit these problems and just continue to give us more practice. So. Okay. All right, let me know if you have any questions.